Hey guys, in this video we're going to address the lab process for titrations. We have done these earlier in the year, so this should be mostly review. We're going to be covering a little bit more about the different types of titrations, whether you have strong acids and bases, weak acids and bases, things like that. So looking at acid-base titrations, remember, we're going to add a solution, either the acid or base, from the burette into the solution in the flask at the bottom. And the concentration of one solution is known, and the concentration of one solution tends to be unknown. So you're trying to find that unknown concentration. The overall goal is to find the equivalence point, which is the volume added to which the stoichiometrically equivalent quantities of acid and base have been combined. So at what volume are the moles of the acid equal to the moles of the base? So remember, equivalence point would be if you added 32 milliliters. You're looking for that specific volume, not the pH for equivalence point. You're able to use an indicator to signal when that equivalence point hits. And an indicator is a dye that will change color at a certain pH range. With our indicator, we will reach an endpoint. This is the pH of the indicator color change. So the endpoint is the pH that matches the volume of our equivalence point. So when doing titrations, we need to select an indicator with an endpoint approximately equal to the pH of the equivalence point of the acid-base reaction. So we need to make sure to pick a correct indicator. So here's showing you that there are tons of indicators that are going to change color at different pHs. So say that we think that our equivalence point will reach an endpoint of about 7 on the pH scale. We'd say, okay, 7, what changes color around 7? So that would be the bromenthal blue or phenol red would be appropriate to use. If our change is more basic, so say phenolphthalein gets used a lot, that would be an endpoint of a pH of about 7. So we would pick that indicator based off of where it's going to change color. So one thing that we can do is we can actually use pH meters and plot titration curves. The equivalence point is going to be found at the most vertical part of the curve. So this is one that you probably saw in Chem 1, just a really basic titration curve. That vertical part is where you have the equivalence point. So our volume that we added was the 100 milliliters, and our end point where they're equal, where the indicator would change color, is at that pH of 7. So we want to go back to some of our basic titrations math. Remember, titrations were all stoichiometry based. So we use stoichiometry to find the equivalence point, or the volume of the titrant required to reach the equivalence point. And we can actually calculate the concentration of a solution from that equivalence point data. So let's look at how to find the equivalence point. So here's an example of when we're titrating 50 milliliters of a 0.48 molars hydrocyanic acid with 0.75 molars of sodium hydroxide. We want to know what volume of base has to be added to react with the equivalence point. So here we do have a weak acid and a strong base. So remember, you need to write the balanced chemical reaction to find the mole ratio. You're going to calculate moles of your analyte, so moles of your known solution. You're going to use the mole ratio to convert the moles of analyte into moles of your titrant, your unknown solution. and use moles of molarity to find the volume of titrant needed. So here's what this looks like. So here we have 50 milliliters. You're always starting with the volume of your unknown. And if we look at the reaction here, hydrocyanic acid and sodium hydroxide are going to be a 1-to-1 ratio, producing sodium cyanide and water. So it's just a 1-to-1 ratio. It's not going to change our stoichiometry. But we do need to start with the volume of our known solution. So the 50 milliliters, and remember we need it in liters, so 0.05 liters. We're going to use the molarity as our conversion factor. So liters goes on the bottom. The 0.48 moles of hydrocyanic acid goes on top. Then we use our mole ratio to change into moles of our titrant, the moles of sodium hydroxide. Then we're going to use that molarity as a conversion to find volume. So if you do the stoichiometry all the way across, we get that our equivalence point should be at 32 milliliters or 0.032 liters. So whenever we're doing a titration, that's approximately where we're going to be looking for that color change. So we can look at the next issue. What's the concentration of sodium hydroxide when 30 milliliters of the base neutralizes 26 milliliters of a 0.5 molar hydrochloric acid, So here we have a strong acid, strong base. So it's still going to be stoichiometry as is, still going to go through the exact same steps. Write our balanced equation, find moles from the volume, use mole ratio, and then use the molarity to find the missing molarity or volume. So our balanced chemical equation, hydrochloric and sodium hydroxide will be in a 1-to-1 ratio, producing sodium chloride and water. We're going to start with volume of our known solution. So we're going to start with the 26 milliliters, but we're going to change into liters, so 0.026, and we're going to use the molarity of the acid to change into moles, so liters on the bottom, moles on top. Then we need to use our mole ratio to change into sodium hydroxide. We did say that was a 1-to-1 ratio. Now this is slightly different than our last problem because we had molarity. This problem we have volume. So we need to actually stop here to figure out moles. So this is going to be 0.013 moles of sodium hydroxide. And remember, when finding the concentration, it's moles over liters. So divide this by the 0.03 liters, and we get that it's a 0.43 molar sodium hydroxide solution. Where this is going to be slightly different is whenever you have an acid and base that are not going to be in a 1-to-1 ratio. So we have 50 milliliters of hydrochloric acid that's titrated with 0.125 molar barium hydroxide, and it takes 12.3 milliliters of the base to reach the end point. So it wants to know the concentration and the pH of the acid solution. So this one has an extra step on there. So we're going to treat this the same. We have our balanced equation. The hydrochloric and barium hydroxide are in a 2-to-1 ratio. We're going to start with our volume of our known solution, which is our base. So the 12.3 milliliters is 0.0123 liters. Change into moles using our molarity. Then we need to use our mole ratio. So remember, it's a 2-to-1 ratio. So that is going to give us moles of hydrochloric acid. To get molarity, you do moles divided by liters. so divided by the 50 milliliters, 0.05 liters, to get a concentration of hydrochloric acid that's 0.0615 molar. The second question wanted to know the pH. Well, remember, since this is a strong acid, the molarity of the acid is equal to the molarity of the hydrogen. So if we do the negative log of 0.0615, we get a pH of 1.211. Remember to use your sig figs that our concentration has 3 sig figs, so our pH is going to have 3 decimals after the period. So looking a little bit more into titrations. There are 3 types of titrations we're going to look at. We've already done titrations between a strong acid and a strong base. New ones that we're going to come across are whenever we have a weak acid that's being titrated with a strong base, and when we have a weak base that's being titrated with a strong acid. For each type of titration, we're going to learn how to write the reactions for it and how to calculate the pH at any point in time during the titration. So we're going to be able to find the initial pH before any titrant is added. At any point between the initial pH and the equivalence point, we'll be able to figure out what is in solution and what is the approximate pH. We'll be able to find the pH at the equivalence point, and we'll be able to figure out what is in existence after the equivalence point, so after neutralization. So initially, you can calculate the pH of the analyte, so the strong acid, strong base, weak acid, or weak base that you're titrating. So remember, if it's a strong acid or strong base, the concentration of the hydrogen or hydroxide is related to the concentration of the acid or base. If it's a weak acid or weak base, remember you're going to have to do an ice table to figure out those concentrations using the Ka or Kb values. And as the titration proceeds, we're going to look on to the next slide to go through what things we're going to be looking at. I know this is a lot. It's a lot of different steps, and there's different steps depending on what type of titration you have. So you're going to write the one-way reaction between the acid and the base. So the acid and the base, what are they going to produce? Whether it's salt and water, whether it's going to be an anion in water, a cation in water, something like that. Using moles, you're going to complete the ice table, but the E stands for end instead of equilibrium. Just at the end of the titration, what do you have? And then the end line is going to determine what you have as your next step. If you have a conjugate acid-base pair that's left over, you can plug into the Henderson-Hasselbalch equation. So this is going to be anytime you have a weak acid or weak base. So if it's a strong acid, strong base titration, excuse me, it is not going to be a Henderson-Hasselbalch equation. This tends to occur before the equivalence point whenever you're using a weak acid or weak base. So this will be at the beginning of the titration. If you're left with only a weak acid or weak base, so it does not have its pair, you're going to write out an equilibrium reaction describing the substance in water using an ice table, the molarities, and the K value to solve for those overall concentrations. Yet again, this does not occur in a strong acid, strong base titration, and this will be at the equivalence point. So before the equivalence point, you're going to have the conjugate acid-base pair, if it's a weak acid and a strong base, or a weak base and a strong acid. At the equivalence point, you're only going to have the weak acid or weak base. You're not going to have any more of the conjugates. Now, if some of the strong acid or strong base is left over, you're going to calculate the pH from the molarity of the hydrogen or hydroxide in solution. This is going to be after the equivalence point where this would occur.